So welcome to the third lecture of Benedict, and today he's going to talk about finite temperature in quantum field.
Exactly. So today, finally, we get to finite temperature. So yeah, just 1 second. Okay, so, but before I do this, let me just again do a quick recap from last time, just to make things clear. Okay, so last time, like starting from this master formula for the effective potential expressed in terms of 1BI functions that I derived, we calculated the one-loop correction to the effective potential for a scalar field. And what we found is, so the effective for some scalar field is given by the tree level potential, which I denote with V naught, and then there's a one-loop correction which goes like 64 pi squared. Let me leave some space here. We'll see first in a second why. So it goes like the force power of the field-dependent mass times a log of the field-dependent mass squared over some RG scale that we had to introduce because we had to renormalize. And the field-dependent mass is given by the second derivative of the tree-level potential with respect to the field. And I derived the 405-4 theory, but I mean it applies more generally. So you can go through the derivation also for generic potentials. I mean, okay. So then I mentioned that this can also be generalized for. So if I now want to calculate, so if my scalar couples to a fermion, say, or to a gauge field, then the fermion and the gauge field will also contribute to the effective potential. And the way you can calculate this is, I mean, it's like the natural generalization. So, so for a fermion and for a gauge field, you also have field-dependent masses. So say for a fermion, it would be, so this was for phi, say, for a fermion. If you have Yukawa coupling, then it would go like this, right? And for U1 gauge field, that was the other example I had last time. Well, there you need a complex scalar, so it's a little bit different, but anyway, it's in principle the same. You have 2 times the gauge coupling. It's the absolute value. So the idea is that kind of if the scalar couples to some other degrees of freedom in your theory, then if it has a non-zero expectation value, this will lead to a mass of these degrees of freedom. And this mass is kind of what you have to use in this formula. So now I can generalize this formula. So I can say sum over the particles that couple to my scalar phi. Let's denote this sum, well, and give it an index I. And then here it's just the field-dependent mass that appears here of the field. In general, I have some number that I will specify in a second. And let's write this like this. And then as we saw, so this kind of counts the number of degrees of freedom. And also there's a potential minus sign for fermions. So Ni is equal to minus 1 to the fermion number. So it's a fancy way of saying it's 1 for a boson and minus 1 for a fermion times the number of degrees of freedom. Right? Remember for a massive vector we had 3 here in front, so this would be 3. For a Dirac fermion there was a minus 4 here, so minus 1 times 4. And then this constant Ci is equal to, as we saw, it's 3 over 2 for a scalar or a fermion, and 5 over 6 for a gauge boson. So it's just like a compact way of writing this. And this typically is called the Coleman-Weinberg potential. So this, I don't know. Okay, and then we applied this to scalar QED. Scalar QED for a massless scalar. And this goes under the name of Coleman-Weinberg model. And then we saw that, so if you have a tree-level potential, so it's a massless scalar, so we only have the phi-4 potential, and it couples to one H field, so it has to be complex, yes?
The fermion number is the number of fermions?
Sorry, this is, I mean, it's either 0 or 1 if it's,
Okay.
yeah, sorry. It's just a fancy way of saying -1 for a fermion and 0 for a boson. So it's not counting fermions, so it's just either 0 or 1. Right, remember there was, I mean, simply there was this minus sign for the fermion in the formula that we had to it. So there's a -1. And then for the fermion there was a 4 because there's 4 degrees of freedom for a direct fermion. So. Okay, so we applied this to the series scalar QED for a scalar with this potential, and then we found that kind of the Coleman-Weinberg correction changes the potential to something. I mean, it takes again the same form, but now there's a field-dependent effective coupling appearing here. So lambda effective was the tree-level coupling plus some number, doesn't matter now, times the logarithm of phi over mu tilde, some RG scale that we had to introduce in the process. Well, it's essentially the scale here, right? So, yes, so this means that kind of the coupling that you have to use in your effective potential is not the tree-level coupling. It is kind of the coupling evaluated according to this formula at the field length. So the coupling that you have to use changes if you move around in the potential. And that's really very similar to, or essentially exactly the same as a running coupling that you know from scattering experiments. Right? So there you have to evaluate the coupling at different energy scales. And here, in the effective potential, you just evaluate at different field lengths. I mean, it's also kind of intuitively not so far-fetched because it's essentially an energy scale, right? The field length, I mean, so a scale. Yeah, and then you have to introduce this. I mean, again, essentially, like for the running coupling, you have to introduce this RG scale to kind of that specifies like your coupling at one scale. And then from there you run it. And then of course in the end things have to be independent of the RG scale. I mean you can specify the coupling at different places and it's all equivalent, right? So okay, anyway, so just to wrap this up, so the big point was that kind of if you, for example, you start with a negative coupling at some RG scale, so your tree level coupling, what you would put in your tree level potential is kind of the quartic coupling is negative, then your potential would go like this, would just be an abyss, right? There's no minimum here. But now, because you actually have to replace it by the effective coupling, the logarithmic term kind of means that the coupling grows and eventually turns positive again. So if this is negative initially, then it should become positive. And you can get a minimum in the theory. So. Okay, and again, this is it's an interesting example, but it will also be, I will later use it for cosmology. And then someone asked me if this also happens in the Higgs potential, and it actually does. So, just quickly, then I start with something new. So the Higgs potential, you also have, okay, now you have a tachyonic mass term. But you also have a quartic coupling. And it turns out the quartic coupling also changes with the Higgs wave. So if I plot Okay, let's just. So I kind of schematically again I use this just as this. It's just 1 degree of freedom now for simplicity. Normally it would be a doublet, right? So I have some quartic coupling here. That's kind of the tree level potential. But now if I include loop effects at one loop order, this coupling starts to depend on the field wave. And then what I see is that so VH. So okay, here you have kind of this wine bottle potential where you have the minimum, right? So it first goes down because of this term, then goes up because this coupling now is positive. But now if you evaluate it to, so this is kind of 100 GeV, our minimum today. But now if you run the coupling up to higher field waves, and this is assuming that you only have the standard model, there's no new degrees of freedom. If there are new degrees of freedom coupling to the Higgs at higher mass scales, then it would change. But assuming there's only the standard model up to the Planck scale, what you find is that the coupling eventually turns negative. So it first crosses 0 and then it turns negative. So, exactly. And this happens at energy scales. It's, I guess, 10 to the 10 to 10 to the 12 GeV. This is, I think, both uncertainties from the measurements of the Higgs quartic coupling, and the top coupling is very important also, and probably also some theoretical uncertainties. I don't know how they play out here. Okay, anyway, so yeah, so if there's nothing up to the Planck scale, we actually live in a metastable. I mean, we live here, right? But eventually we'll go here, which is very bad. So if you're getting worried now, people have calculated this. It turns out that the lifetime so we would then just be in a metastable vacuum, so eventually we'll tunnel into this vacuum, but the lifetime is many, many orders of magnitude larger than the age of the universe. So but, I mean, there's a non-zero probability, very small, but non-zero that may happen next minute, right? I mean,
So actually people were afraid when the LHC was turned on.
that it may trigger this,
Yeah,
right?
yeah.
Yeah, exactly.
Triggered that.
Well, there was also the black hole scare, right? People were also...
The black hole, yeah. I think people were scared of the black hole.
And also this, yeah.
And also that.
Yeah, there were actually lawsuits trying to prevent the LHC from starting because of that.
Because of the black holes or because of the black holes?
I thought the black holes, but...
It's probably the black holes.
Yeah.
Which are harmless anyways.
Yeah, there's a long report from CERN showing that even if they are produced, they would be harmless. Yeah.
Yes.
So just if you're interested, this is one reference where this has been.
Just to emphasize what Benedict said, the reason why it goes down is because of the top quarter mass. There's a negative contribution because of fermion.
Yeah.
So it depends, it's very sensitive to the measurement of the top quarter mass.
Exactly. So
it's very interesting. There's a sliver character space where your math is stable, and that's where we are.
exactly, it's a bit weird because exactly. So there's kind of there's these nice plots which show like there's a region in the top coupling Higgs mass space where we are metastable, and it's a very small region, and we are exactly there. So, and nobody really knows why. I mean, maybe there's some deep reason, or maybe it's just coincidence.
The last number is 1?
6, sorry. 3536. Yeah, there's other references. This is the first one. Yeah. Well, there's also one that is very highly cited. So, okay. Yeah.
People say that have this metastable state because the Brown formal conditions from the potential, but in the 70s this time model wasn't complete, and now we can add bosons to become positive, so it doesn't exist this last curve, right?
Sorry, say it again. So this doesn't exist, you say?
Because we can add bosons to add positivity to the bound from low condition, right? Or
I mean, so again, this was assuming that we only have the sum model up to the Planck scale. If that's the case, that's a valid theory, right? Then this is what happens. So this you can calculate. Now, if you have some new particles at some high scale, then it would change. Right? So
this result is one loop result.
I think two loop. They do.
So it's still
Yeah, but I think, yeah, probably they estimate the 3 loop and think that it's not going to change the result, but I'm not, yeah.
Surely not true that you don't know the result.
No, of course not, right? I mean, you can
Maybe non-analytic in the coupling.
No, I mean, no, you have to go loop order, right? So, and then, of course, you expect that it kind of converges. I mean,
Not necessarily, because not the whole, infinite loops doesn't mean non-perturbative.
all right, okay. I don't know. I mean, I think the opinion is that, like, the 2-loop result is a good estimate.
It's opinion.
Yeah, but I'm not an expert on this, so I mean, don't ask me really, but I mean, I'm just.
I think the couplings, they don't get large, right? Lambda actually crosses.
Yeah, the couplings don't get. That's your point. You're saying that kind of that. Yeah, I guess the couplings probably stay small. Exactly. So I mean, okay. Eventually, of course, if you keep going down, they will become big. But probably that happens after the Planck scale or so, where you don't know what happens anyway, right? So yeah. So this.
So one more historical remark, because I'm old, I can.
Okay. Yeah.
You know, you can think the only parameter in the standard model that has dimensions is this n that he wrote there. So you could imagine, suppose you start with the standard model, quote unquote, without any mass scale. So m equals 0. The question is, can you generate symmetry breaking because of the Coleman-Weinberg?
Exactly. That was the original idea. Exactly. So.
And the answer is you could, but you can't. You could, but it doesn't work because the top mass is not heavy enough, I think, or I forget. There's a reason why.
You're saying you can't even, so I see, yeah, I'm not sure this does.
The numbers don't work.
But I mean, the Higgs mass would also not work out, right?
Yeah,
so,
yes, I
exactly.
think the Higgs would not work.
Exactly.
The idea is nice. See, you start the standard model without any mass parameter, so really scale independent at 3 level. Then, of course, at loop level is not scale invariant, as Benedict showed last time. And you can imagine whether you could trigger electric symmetry breaking the right phenomenology.
Exactly, yeah.
And you can't, because of the values of the top quark mass, etc.
Exactly, so,
The idea was beautiful.
yeah. Yeah, this was, I think, the original motivation.
It
right,
was
to-
the original motivation.
I have a question. So at the beginning for H very small, this effect isn't very large. Like for small.
Sorry, what is not very large?
For small H, the effect is not very large.
Yeah, exactly. So,
It's barely, because otherwise the measure of the H mass would be different.
exactly. So, exactly. The fact here, I mean, you see it happens at like many orders of magnitude away from our medium, right? So you have to run a long time. I mean, it runs roughly logarithmically, right? So it takes a time until it has a big effect. So.
So the H mass is the right H mass to measure.
Exactly. I mean, so the Higgs mass is anyway. The Higgs mass is kind of so. You have to take this effect into account to kind of calculate the quartic coupling that you need to get the Higgs mass, right? So that's kind of the right way. I mean, the quartic coupling, like say at this scale here, is really what is measured at the LHC, right? So, I mean, with the additional input of the Z or W mass and things like that. Okay, so actually let me leave space here. Okay, so far everything is at 0 temperature, but since we want to discuss phase transitions in the early universe, and it's hot in the early universe, we need to include finite temperature effect. And to this end, we will derive a finite temperature version of the effective potential. Yeah, and just to warn you again, I mean, so it will be like last time, there will be some concepts along the way which may be a bit difficult to swallow at first if you haven't encountered them before. But bear with me, because in the end, once the dust settles, there will be a nice formula. But anyway, I hope the derivation is also clear, so, but just to prepare you to be attentive. So, okay, let's first recap a little bit of statistical mechanics. So we are interested, like so we're going to replace the vacuum that is normally considered in QFT, and that is appropriate, like for scattering experiments, for example, by thermal plasma, right? At some temperature T. And in quantum statistical mechanics, this is described by the canonical ensemble. And let's first start with quantum mechanics. To recap, so the crucial quantity is the so-called density matrix. Let me just write down. So there's the so-called partition function. You probably all remember this, but anyway, just to set the notation also. And then I have this Boltzmann factor, where beta is 1 over the temperature, and H is a Hamiltonian, right? So now let's expand this into energy eigenstates. So psi m is now eigenstate, an energy eigenstate. And that's an energy eigenvalue. Should read a little bit, and it's pretty clear. Okay, so this density matrix is kind of normalized such that the trace of this object is 1. So, and this is what determines the partition function. So the partition function is now given by the requirement that the trace of rho, no, sorry, what am I saying? No. So the requirement is that the trace of rho is 1, and from this we find that the partition function is given by the trace of this object, and now if I do it in energy eigenstates, well, now I sandwich it between these states here, and then I find it's just this expression here, right? Actually, sorry, let me derive an intermediate step because it would be useful. It's trivial. So I sandwich this between. So, I mean, I can choose any basis I want for the trace, but now here I choose this basis of energy eigenstates, so it's like a complete orthonormal set of states in a Hilbert space. And so if I evaluate this is what I get. Okay, so far so good. And now if you want to calculate some ensemble averages of some operator, O would be given by, so the ensemble average is given by the trace of the density matrix times the operator, right? I mean, yes, okay, and then if I evaluate it, it's 1 over z, the partition function. Okay, I guess it's all. It's all familiar, right? So, okay. So this was quantum mechanics, but now, of course, we are interested. Can you erase this already? I guess we are interested in quantum field theory. So now let's go from quantum mechanics to quantum field theory. Ah, damn it, I erased the expression that I needed. So, rewrite it again. Wasn't very smart. So, okay, so, and the first thing I want to calculate is the partition function, because the partition function already contains a lot of information, and in particular I can get like lots of ensemble averages by taking derivatives with respect to the partition function. So for example, I take the derivative with respect to beta, I kind of get the ensemble average of the Hamiltonian, the average energy of my system, things like this. So the partition function is containing a lot of information. Okay, let me write down the formula for the partition function in QM again. And then we start in earnest. So it's a trace of e to the minus beta h, which is the sum over some states. I chose it to be the energy eigenstates, but again, it can be any complete orthonormal set of states that I sandwich this operator in between and sum over all states, right? Okay, so this is in quantum mechanics. And now in QFT. In QFT, we don't just have a discrete set of states. We have a continuum of states generically, right? I mean, it's like a whole Fock space of states, like many particle states, potentially even non-perturbative objects, like solitons, stuff like this. So what we have to do now, the expression is very similar. So I can again write it as like some trace over e to the minus beta times the Hamiltonian of my quantum field theory in this case now. But now, since I have the continuum of states, I have kind of like an integral over all different states. So it's just a natural generalization from a discrete set of states to a continuum of states. Okay. And now what I will do is I will derive a path integral representation of this partition function. And this will be useful mainly for, when you will see, it will teach us something about how to think about quantum field theory at finite temperature, how to evaluate quantum field theory in finite temperature. So that's the main reason of this exercise. And the starting point is, let me write this here, the starting point is Feynman's path integral formula for a transition amplitude. So I'll write it down first. Well, let's do this here. Take some space. So this is, okay, let me erase this and then write over the other side, because otherwise it's a little bit difficult to do. Okay, so this is the transition amplitude from some field configuration phi a at a time ta. So like Q of t state at time ta to Q of t state at a time tb, as you can guess. And again, that's a Hamiltonian of my theory. And this can be written as a path integral in the following way. So here, these are operators, these are states in my Fock space, or my Hilbert space. On this side, these are all classical fields, right? The usual usual step in path integrals. So I have an integral over all possible field configurations. But now they have boundary conditions, and the boundary conditions are that phi of TA x is this configuration phi A, so like the classical field that corresponds to this state. The classical field configuration, and phi of TB x. So I have these boundary conditions for my path integral, and now I have a phase. So the time integral goes from TA to TB, and then there's also the volume integral that I don't specify, and the Lagrangian. I guess this you've probably all seen before, right? This is kind of the starting point. From this you can derive the path integral representation of correlation functions in PFT, for example. So, and it's like the kind of the natural generalization of the path integral in quantum mechanics. Right? In quantum mechanics you would have like some initial state xi, some final state xf, and then you integrate over all paths between these two states as example. Okay. So, but now you see that like this and this already look quite similar, right? So, and we can actually make them exactly the same by doing the following steps, which are maybe sound a bit far-fetched, but I mean it's really just, you can think of it just as a mathematical trick to and here I'm thinking about, for now this is just a scalar field theory, right? So I'm not, okay, so in order to kind of make this side and this side equal, and to get a representation of my partition function, I have to do the following steps. So to obtain path integral representation of Z, need to do the following steps. The first step is, so you see that here I have e to the minus beta, here I have e to the minus I TB minus TA. So first thing I will set TA to 0. This is just, I mean, I can just, can everyone read or shall I, yeah. So I will set TA to 0. Okay, that's not much. But now, I will identify I times TB with beta. I times TB equal to beta. Okay? And it's convenient to kind of introduce, so now I can introduce some kind of imaginary time. I call it, so let's call this tau b. So let's more generally, let's call I TA equal to tau. And that's an imaginary time. So this corresponds to this equivalent of the Wick rotation that you know for energies, where you kind of rotate the integration from the real axis to the complex axis. This is exactly the same. So here you rotate from integrating over some real times to an integration over complex times. And this is a part that may be a bit hard to swallow. So this is what I was warning you about. Okay, let me just continue a little bit, and then I can maybe say a bit more about this. So, okay, this is one step. So then I can make this expression the same. Now the other step is that I have to take the trace over these states, right? So first of all, I have to identify phi A, and phi B. So phi A of, and let's go already to this complex time. So phi A. Let's write this. Identify. So phi A of some time tau A x, and we set phi tau A to 0, so it's just has to be the same as phi B, the other configuration, at the time tau B x, and you see tau B now goes, so tau B is beta, right? So again, the third step is that I have to build the trace, so I identified them, now I have to integrate over them, right? Like this step. So I have to integrate over, say, phi A of x. Sorry, the way I wrote it is not very good. Sorry, I should. So this is phi A of x is defined as the field at tau A of x, and this is what I called phi B of x. It's this way. Okay, just remember this because I will run it now to have some space. But okay, do these steps. What I get is that d phi A e to the minus beta phi A is equal to the path integral now. So now I have to integrate. So again, here I kept these configurations at the initial and the final time fixed. But now I only have to require that the configurations at initial and final times agree, and then I have to integrate over all configurations. So my new boundary conditions are that phi of tau equals 0, x is the same as phi of tau equal beta x. Okay, and here I forgot a step. So where did I do? Ah, yeah. So, okay, I made this formal identification, right? ITB is beta. And now it's convenient to so essentially I'm integrating in this, on this side I'm integrating from TA equal 0 to TB equal minus I beta, right? So if I draw the complex plane, my time direction, the real part, the imaginary part, in standard quantum field theory we integrate, say, from some initial to some final time on the real axis, but to get this path integral representation of the partition function in final temperature quantum field theory, I have to integrate like from T naught equals 0 to T naught equal minus I beta, right? So this is okay, and yeah. So and then it's, as I said, then it's useful to just define a new time variable tau as I times the normal time. And this is again like what we do in the Wick rotation, right? We introduce like a new P0 component that is I times the original P0. Okay, and if I do this, then, and this is the thing I didn't say, then, so where do I write this? Okay, let me write this here. I hope you can read this. So, for example, if I have a Lagrangian now, is this readable? Or it's a bit too low, I guess, right? Okay, let me write it here. That's better. So, say I have a Lagrangian d mu phi for a scalar field, and then this is kind of dt phi squared minus di phi squared, right? The Minkowski metric. And now, again, I introduce this new rotated time variable tau, so I can write this as this. The kinetic term now becomes, because I have I squared here, right? So it becomes d minus d tau phi squared, right? So, meaning that now all the derivatives are just added. So I now live in a space where the metric is just 1, 1, 1, 1 in Euclidean space, right? So then I can write this as, so L after this rotation goes to, I can write this as minus a Euclidean L, where the Euclidean L is calculated just, it's just this, right? D tau phi squared plus di phi squared plus a potential. So this is what I call the Euclidean Lagrangian. It's Lagrangian in Euclidean space. Okay, and this is what enters here. So this is like kind of what I forgot. Okay, and that's it. So again, to recap, to obtain an expression for a Poisson expression for the partition function in quantum field theory, I had to do, well, essentially 4 steps. I first identify I times the final time is beta, so meaning that I now integrate along the negative complex time axis. And then it is useful to introduce a new time variable tau b, which is just I times the original time variable. And if I do this, I see that kind of my metric is now the one that I have in Euclidean space, right? Again, it's exactly the same that I have in the Wick rotation of the energy. Okay, and then I need to identify initial and final state, because I'm taking a trace. And this means that my field has to fulfill the boundary conditions that kind of at the initial time, tau a, which I set to 0, I can just choose this. It's the same as at tau equal beta. Okay? So it has some cyclic boundary condition. And then, then I had to take the trace, which means I have to sum over all configurations phi a. So, meaning I sum over all fields phi that satisfy these boundary conditions. Okay? So, what does that mean now? It means that we are now, because we are imposing these cyclic boundary conditions, it means that my time variable. So the fields are cyclic in my time variable, so effectively the time direction is compactified. So I can now draw it like this. So this is kind of, this is the 3D space that goes like on till infinity in both directions. Of course I cannot draw this. And then this here is my new imaginary time direction. And this is compactified. So this is kind of like my field theory now lives on, so because I'm imposing cyclic boundary conditions, right? So it means that like if I go from 0 to beta, so I can say I start at tau equal 0 here, and then I go around until tau equal beta, and they have to be the same, right? So did any one of you already encounter extra dimensions? No, that's, I mean, so in like...
Nobody has encountered extra.
I saw them.
Not yet.
I saw them. I can show you.
Oh, okay.
Okay. Okay. Are there any questions? Again, as I said, this may be a little bit difficult to swallow, but yes.
One part that I wasn't sure in which you could identify this path integral with the partition function was for me that when you're calculating these path integrals for transition amplitudes on the right there, these are space-time integrals, whereas for partition functions, you're presumably just integrating on a Cauchy surface, also over many different configurations. I don't see why you can identify this space-time integral with an integral that presumably just should be in space.
Sorry, no, I mean, so you integrate, sorry, you're saying, I'm not sure I understand. So, I mean, I'm taking the trace, right? So I have to integrate over all
space.
field configurations, right? So,
yeah, exactly. So field configurations should live in some, Hilbert space in some Cauchy hypersurface, not on the entire space-time. Well, maybe I'm missing something.
yeah, but this is exactly what I'm doing here, right? So this is why I'm effectively on the other side getting out compactified time, right? So I'm kind of, I'm not integrating, you're worried that I'm integrating over...
For the transition amplitude that you're integrating over paths, over space-time, where
exactly.
For the partition function, it seems to me that you should just integrate over a Cauchy hypersurface.
Fixed in time, you mean?
Yeah.
Or, yeah. But I think this is exactly, so this was really just like a formal modification of both sides of my relation, right? So I think what you're saying is kind of essentially that, I'm not integrating over a fixed time, I'm integrating over configurations that live on a compactified time direction, so you're right, there's no notion of time here, right? These are all like, I'm in equilibrium, so it's kind of, I think what you're saying is correct, but I think the outcome is exactly this, you still have a finite integral over a time direction, but it's a compactified imaginary time. So this is.
I think I'll have to think a little more and convince myself.
Yeah,
So I think something relating to what he's asking is the transition of the Minicourse geometry space-time of the group is 3-1. And after the compactification of that, you go to the S4 geometry.
Exactly.
Yeah, so that's, I think, that's
exactly. So you go to exactly. So we are in Euclidean space. So we don't. It's not a normal time direction. Plus, it's compactified, right? So it's kind of. Yeah, I think the way to think about it is really just a mathematical trick to kind of like get an expression that you want. Okay. Any other questions, or shall I?
thought that actually I right is temperature, and I guess you could keep the time dependence. Like instead of writing it there, you write it.
Exactly. So you can, in general, keep time dependence, but then you have to use a different formalism. So, at least if you want to do it straightforwardly. So this is the so-called. It goes under the name of imaginary time formalism. And this requires, to my understanding, that kind of you look at time-independent quantities, so which is enough in equilibrium, right? Generically.
It's like thermal equilibrium, right? You're in equilibrium.
Exactly.
Everything's time.
If you now want to study time-dependent quantities, then there's a so-called real-time formalism, and there's also closed time-path formalism. So these allow you to study like time-dependent phenomena, and well, the closed-time formalism at least does. But yeah, here I'm just looking at time independent. So actually we'll see. So now so the next thing I will define is now we can define correlators. So the next thing is, so again, in quantum field theory, we're usually interested in correlation functions, so time-ordered products of some field operators, and this I can also define now. So these I define as, again, like I'm taking the ensemble average. This is like a one example of like the ensemble average of an operator, right? The formula I had for the case of quantum mechanics. So I'm taking the trace of my density matrix times my operator. And yeah, so for this imaginary time formalism, like these all have to be evaluated at the same time. And then this path ordering here that you introduce is kind of a path ordering in the complex time direction. So that's why I introduced this lower subscript C here. So they can have different, a priori different arguments along the complex time direction.
So is it the same time or is it different times?
I mean, this is now, again, this is so this is same real time. I mean, in principle, I can keep the time variables complex, right?
Yeah.
So they have to have the same real time. That is like the physical time.
And then they have the same complex time as well, right?
No, they can. I mean, so a priori, I guess they could live. I'm not sure what this is used for, but I mean, a priori, they could live on. So again, so in normal QFT, you have correlators at different real times like this, right? I mean, these have to live at the same real time, but now they could have different complex time arguments. I'm not entirely sure what this is used for, so I'm not, but okay. Anyway, this is also not. We will actually not need. So yes, here. Oh yeah, now I can continue here. Okay, so I can introduce these correlators, and now I can find in very same way. I can find a path into representation of these correlation functions, and again, like in quantum field theory and zero temperature quantum field theory, I can define a generating function. So I define a generating functional as again, I'm integrating over field configurations which are cyclic in this imaginary time direction. And I have the same factor as before. And okay, sorry, I introduce a source term again, same way as I do in standard zero temperature quantum field theory. So this is the same expression like as for the partition function, but with the addition of the source term here. And so now I can take derivatives with respect to the source, which brings down the field, and this essentially builds up these correlation functions. So I find the following relation. The ensemble average, the correlation functions in a finite temperature QFT are, let me just write it first. So this is exactly the same formula that we had in zero temperature QFT, right? I take just derivatives of this correlation of this generating functional with respect to the source, and derivatives for an endpoint function. I set the source to 0, and then I divide by the partition function at 0 source, which is the partition function, right? And okay, so now I have a generating functional, and now I can go through the same steps as we did before. So from the generating functional, now beta, always I write superscript beta to make clear that it's the finite temperature version. I now do a Legendre transformation with respect to the classical field phi bar, which is just the ensemble average of my field operator phi, which I can get from the first derivative of this functional w with respect to the source. And w beta is given by just the log of z of j beta. So this is exactly the same thing that we had in zero temperature QFT. We can do the same step now. So we perform a Legendre transformation with respect to this new field variable, the classical field, the ensemble average of my field operator, and this gives me an effective action as before. Okay, and now let me write this again here. So now from this effective action, I can I can restrict to constant field configuration. So where phi, and this is a generically like space-time dependent, well, not space-time, space-dependent, I guess in this case, field. I specify to a constant field. It's independent of x, and I get the effective potential at finite temperature. So I'm going through the same steps as before. I will not repeat them now. Right? So, and now I can also, again, I can derive a representation of the effective potential in terms of 1PI functions. Again, the same as before. Using the fact that, again, this generating functional here, the effective action here, is the generating functional of 1PI functions. So using this information, I can obtain a representation of my effective potential in terms of so this C here is always to denote that it's a constant field. I mean, the literature oft refers to classical fields, so just don't get confused. In my lectures, it just means that it's independent of space. Okay.
Does it depend on the temperature, phi c bar? Because it's derivative of...
I mean, generically, I guess it could, yeah, but I mean, this is constant, right? So it's not...
So it's an assumption that it's a constant? And it's a constant in the x and also dependent on temperature, right?
Exactly, generically. Well, I guess a good question, I'm not so sure now. No, but I mean, I don't think you can just identify the complex time variation as temperature, right? So this is just, I mean...
Yeah, okay, my only question is because the definition of phi bar now has the temperature in it, right? Because
I mean, the effective potential definitely depends on the temperature. The field does not. I mean, the field is really just a constant.
Right, but the definition of phi bar has a temperature in it. No,
Well, it has a dependence on the complex time variation, right? So,
no, if you go down,
no, I know what you mean. So, I mean, it has essentially, there's a x0 dependence here, right?
Right.
So, I don't think you can identify this with a temperature. I mean, this is not the temperature. It's just kind of. No, this is constant. I mean, so like I mean, this is not temperature dependent in itself. So, but it's really like a constant field configuration. Right? Yeah.
It just seems that there's a knob there because when you define phi bar as the ensemble average, it's a temperature dependent statement because the ensemble is a temperature equal.
Yeah, but I mean, this is exactly what I want to. Exactly, this is what I want to. Of course, okay. So I have. Yeah, I'm not sure what you. I mean, of course, the field potential will be temperature dependent, right? And the ensemble average will also be temperature dependent. I mean, I guess isn't that the same thing? So.
Yeah, it is the same thing. Yes.
Yeah. Okay.
I think I get it now. Yes.
So I can get it. Because W depends on Z, and Z depends on beta, right? Because okay. And then if you define...
Yeah. So exactly. So this is. I mean, of course, this is. I mean, this is a temperature dependent ensemble average, right? This is really just this object here, right? So.
Yes.
I mean, so.
Phi bar is at a given temperature beta. That's it.
I mean, phi bar.
Constant, but at a given temperature beta.
Exactly. So phi is really the ensemble average, right? So it is e to the minus beta h phi, and then sorry, the way I should put it is different. It's a trace of this, right?
Yeah.
So yes, it is temperature dependent, of course. So it's a temperature dependent. Yeah. I guess that's fine, right? Or yeah. Okay, so okay, let's press ahead. So, okay, now we have this formula for the effective potential that follows exactly in the same way as before. Okay, so this is kind of the same formula that we had before, but now I have, instead of the normal 1PI functions that we have in zero temperature QFT, I have some 1PI functions at finite temperature. So the question is now, how do we calculate those, right? So this is kind of that's the step that we have to do. And, oops. Yeah, so as you can kind of see from this picture. Okay, now let me first remind you what these. So I can again represent those in terms of some Feynman diagrams, the usual sum of 1PI diagrams. Okay, and let me just give some examples. So let's again consider phi to the 4 series. And I write the one in Minkowski space, and then later once we rotate in the Euclidean space. But so I'm looking at phi to the 4 series, so I have the mass term, and I have a quartic coupling. And then, so then again, we have, I can draw Feynman diagrams. So how do we do? Yeah, let's do this lower. So the lowest function is with two outer particles. This is just a propagator with some mass insertion like before, and a one-loop correction, and then the high loop corrections. So I'm essentially just repeating the same thing that we had before. So for the 4-point function, I have the vertex, that's a tree-level contribution, and then I have a one-loop correction and some high-loop corrections that we don't care about. Okay, and then for the 6-point function, for example, there's no tree-level contribution, but there's only the one-loop piece and high-loop pieces, and then for the 8 and higher point functions, it's the same. So this, the representation in terms of Feynman diagrams is again the same. It's a sum over all 1PI diagrams. But the question is now, what are the Feynman rules that I have to use here? So now, of course, it's not the same Feynman rules anymore that we had at zero temperature, right? Then we would end up with the same object. This cannot be. And so I will not derive this, but just to kind of motivate it, I mean, like looking at this picture, it's actually clear what will happen. Namely, so as I said, we have a quantum field theory now that lives not in Minkowski space, but in Euclidean space to account for finite temperature, and the force direction, which was before the time direction, is compactified. So, and now if you go to Fourier, if you Fourier transform, then you find, so go to, essentially go to momentum space. So we Fourier transform, so we have some field tau x. So the space direction is still like as before, so we just have an integral of our momenta cubed. But now the time direction is compactified. And so if you have a field living on a circle, you get a discrete set of Fourier modes, right? So you get a sum over, so it goes from minus infinity to infinity, over a set of frequencies. So you can add this here plus I omega k tau. And now I don't have space anymore. So let's move this here. And then I have the field in momentum space. And this now depends on the momentum and these discrete set of modes. So I could just, in principle, I could just use the k here as a label. And then there is a factor of beta minus 1 in front, just for dimensional reasons. And these are called the so-called Matsubara nodes. Okay, and then, so again, like from, I erased it now, but the requirement was that kind of if I go from tau equals 0 to tau equal beta, I get back to the same field. So I can phi of tau equals 0 x to be equal phi of beta x. And then you see that this is fulfilled if omega k takes on integer values. So omega k is given by there's a convenient normalization. Well, there's a normalization factor. Oh, sorry, you need this 2 pi exactly. K beta to the minus 1. That's essentially it. So I mean, this was kind of the reason why I went through this to derive this path integral representation of the partition function was to show you that it is obtained by exactly making this identification, so by going to Euclidean time, and compactifying, which means that I'm making this identification, and then I find that my field now consists not of a continuum of modes, but of a tower of these so-called Matsubara nodes. And now it's actually easy to guess what happens to the Feynman rules. Exactly. So now the Feynman rules, how do they change? And again, I'm in 5-4 theory here, so that's what I'm looking at. So for a propagator, I normally have this expression, right? So now there are two changes. One is that I go to Euclidean space. So this becomes a Euclidean momentum. So I can write it as like, I get an overall minus sign here in front. Right, so P squared equal goes to, because I have to do that, so I did the Wick rotation for the time direction, but now to be consistent, I also have to do it for the momentum direction, and I get exactly like for the usual Wick rotation, I get this. Sorry, what? No, sorry, this. This is equal to this, which is equal to minus Euclidean momentum squared. So this is one change, and then now the second change is that these energy states I can have are discrete, right? So I get essentially I get a minus sign, and now I get these frequencies here plus a normal 3 momentum plus a mass squared, and I can forget about the I epsilon because I already did the Wick rotation. Okay, this is one thing. Okay, for the vertex I get the same, so a vertex gets a factor of minus I lambda as before. And then the second change is that before I had to integrate over the momenta. And now, of course, there's no continuous set of energy states anymore, but there's this discrete set, so I have to sum. So I get a sum over these Matsubara modes, over these k states, and I integrate over and I get a factor of I over beta in front. You can check that. So essentially, you can use, if you want to see how this transforms, exactly. So you can think that you first write P naught as I P naught E. Now, if you think of this as a discrete variable, at first you would get 2p I k. So you can change kind of your integral, your dp0 integral to like a dk integral, and then you get a factor of 2 pi, which compensates one factor of 2 pi in the denominator here. You get a factor of I over beta. Okay, and then in the next step you take a discrete and you get a sum. Just to make clear why there's one factor of 2 pi less here, and there's a factor of 1 over I over beta here. Okay, and that's essentially it. So
Sorry. When we do a recrutation, don't we need to do a minus I recrutation on the energy?
yeah, it could be that I got the wrong sign here.
So that
No, because no, it's
the same.
I from. Yeah, you're right. I'm not sure I got the sign. So you're saying I have this? Yeah. Okay, I'm not sure. I think the sign is correct. I'm not sure how this comes now. But yeah, you're right. I mean, normally you have. I mean, exactly. So you direct from minus infinity to infinity along the real axis, and then from minus imaginary infinity. Exactly. Yeah. Okay, I'm not sure now how the sign works out here. But this sign should be correct, so I'm not sure what happens here. Okay, I can check later, sorry. Okay, so do I still have time? I'm taking a long time.
10 minutes.
Let's see.
Give or take.
I'm not sure. Okay, now I can probably at least get to some final expression here. Okay, so let's leave this. Okay, so this is kind of the main intermediate result, that we again calculate the effective potential by summing up these 1PI graphs, but now we have this new set of final rules because that's what happens at finite temperature. Okay, so now I can again kind of, let me split this, let me call these the one loop contributions, let me denote them with a 1 subscript. And these are always the momenta 0, the outer momenta. Okay, and again, I essentially get the same as before, so I have this numerical factor that counts the number of diagrams that I have to include for a given topology. Before I had a d4p integral, but now I have to replace this by the sum of the Matsubara modes and the 3-dimensional momentum integral. And then, so here's a factor n. So I get for each vertex, I get a factor minus I to the lambda, times lambda. And then the propagator is right? So this is exactly, I mean, I'm using the same expression that we had before at zero temperature, but now I just use this new family rule. So I have this integral, the d4p integral becomes this, the propagator now becomes this, the vertex is the same. So again, it's kind of for each, so n counts the number of vertices I have, right? For each vertex, I have 2 fields, and for each vertex, I have 1 internal propagator, right? So to close the loop. So each vertex comes, each n comes with 2 outer fields and 1 propagator. Yeah, so each vertex comes with 1 propagator and 1 vertex factor. Okay, and now essentially we can do the same steps as before. So now the effective potential is given by, there's again the tree level contribution, which is arising from these 2 pieces here that do not change because they don't have a temperature dependence. And now I get a sum over all these 1pi pieces. So tutorial. Right, this is again the formula. Well, now I erased it, but anyway, this is just the master formula. So now I plug this in here, and I can evaluate the sum, and I get a log as before. So everything is really more or less the same, except that now I still have this sum over the Matsubara nodes. Okay, I guess you probably remember, I mean, I'm doing the same as before. So not much changed, except for some details. And now I can write this as p0 of phi plus the one loop contribution, let me call it p1 of phi. And then there's some constant that does not depend on phi and that I don't care about. And what I'll do is so essentially, again, the same thing as before. I write this as the denominator. So I put it here, denominator plus this divided by the denominator. And the denominator here does not depend on the field. So it's a constant that I can throw away. This is what I call the constant here. So the one loop contribution to the effective potential that I really care about, I can now write it like this. Let's call this omega k squared plus p squared. So I've again introduced this field-dependent mass here. It's just the tree-level mass plus the contribution that I get in the non-zero background for phi. Right? So I write this as omega k squared plus p squared plus m squared plus this piece, and then m squared plus this piece I call m squared of phi, and I get this. Okay, now we are almost there. So now I use the same kind of trick I used before. I do not evaluate this guy here because it's badly divergent. But I will take the derivative of this expression with respect to, let me call this omega squared. So the 3D momentum squared plus the field-dependent mass squared I call omega squared. And now what I evaluate is the derivative of this potential with respect to omega. So this, and then if I integrate, I get kind of back the potential. I potentially miss some pieces that are independent of omega, right? But I mean, if they're independent of omega, they're independent of the field, so they're just a constant, so we don't care. I mean, okay, so I take the derivative. I should write it like this. I take the derivative of this object here with respect to omega, so this just gives me this in the denominator, so I get to beta minus infinity to infinity d3p cubed, and now there's this factor omega k squared plus omega squared, and then there's a 2 omega in the numerator. Okay? And now I use the fact, so I use this formula here just to write it in terms of k, which is really what I'm summing over. So I use omega k squared is 4 pi squared k squared beta to the minus 2. I plug this in here, and now you can just use Mathematica if you want and put in the sum or look into some tables. And you find that it sums to a nice expression. And this is, what you get in the end is the d3p integral we haven't evaluated yet, right? d3p 2 pi cubed. And I write it in a way that is kind of convenient for the next step. So it sums to this expression here. 1 plus 2 times e to the minus beta omega over 1 minus e to the minus beta omega. Maybe a bit surprising because it looks a bit ugly, but that's what happens. Okay, and I will stop in a minute. So I'm almost, because I think there's a nice point to stop in a minute.
That's omega k.
Hmm?
And you sum over that.
I mean, omega k, like,
Summed
is,
over k.
I summed over k's already, and then I get this expression. So k is gone. Okay, so then should actually, maybe to make clear, so that's temperature dependent, put the beta here. Okay, so now I take this expression, I have to integrate it with respect to omega, right? This gives me just an omega here because it's a constant. And this one, you can easily see it's just the log of this denominator.
Wait, is this for omega going to 0? All of them are 0.
For omega going...
Before you make the something, no? If you send omega to 0?
If I send omega...
Basically because there is a k equal to 0.
Sorry, what's your... I mean, yes, if I send omega to 0, it will go to 0, but...
Then all of them are 0, but then there is k equal to 0.
Exactly, so there's also... because you're saying that kind of... Because here it doesn't...
It blows up for omega going to 0.
Exactly, it blows up for omega going to 0, but this is exactly because you have the k0 contribution. Right?
Yes.
Exactly. Exactly. So, okay, I'll integrate this, very simple, and what I get is, let's write it, and then stop for today. I get omega over 2 plus 1 over beta, and then the log of 1 minus e to the minus beta omega. And just to remind you again, omega squared was the 3D momentum squared that we still have to integrate over, plus the field-dependent mass. Yeah, and this here is plus omega independent terms that I missed because I took the derivative with respect to omega. But we don't care about those because they don't depend on the field, so they're just a constant. Okay, and this is almost it, but I think, yeah, let's stop here. So let me just point out, so there's two contributions now. One depends on beta. Beta is one of the temperatures, so one is temperature dependent. That's kind of a thermal correction to our effective potential. And then there's this piece here, which is temperature independent. And now you can kind of guess already what this will be. No? I mean, it's exactly this what I will show next time. This piece is exactly the Coleman-Weinberg potential that we derived already. So you can kind of manipulate it. It's a few lines, but I'll do it next time. So this is the Coleman-Weinberg potential at zero temperature that we derived already. This master formula I started with at the beginning of the lecture. And this is kind of the correction that you get at finite temperature. And yeah, I will show you that you cannot actually you cannot simplify this much more. In the end, you will write it over as an integral, which you have to evaluate numerically. But yeah, so this is essentially already the expression that you get at the end. Yes?
When you say that the omega number 2 is the Coleman-Weinberg, you mean the scale invariance?
I mean, not so. In the general formula I had at the beginning. So remember, this was. So I had the Coleman-Weinberg potential and the Coleman-Weinberg model, right? So the Coleman-Weinberg potential is just this general expression. So V1 is 1 over 64 pi squared m of phi to the fourth power for the scalar now, right? So log of m squared over some RG scale minus 3/2. That expression is what I mean. And it's not, I mean, you don't see it immediately that this guy would give this one, but I will show this next time, so. Okay. Okay, and then once we've done this, we have, then essentially we have a recipe. So then the derivation, you can forget about it if you want, and you just have like simple formula for how to calculate the both zero temperature loop corrected plus thermal loop corrected potential at one loop, which is like this piece plus this piece, which you have to evaluate numerically. So, okay.
More questions?
There's a step in the calculation that you assume that the external moments are all zero.
Yeah.
And this to me is puzzling because I think of like the initial part was being a thermal bath, and they have a momentum distribution. And this momentum distribution is somewhat related to the temperature.
So the external momenta are zero, right?
Yeah.
The internal momenta are not.
Yeah.
And this corresponds to the fact that I have kind of that I evaluate. Essentially follows from this representation of the 1pi function in terms of the effective potential as a generating function of the 1pi functions, right? So you are saying you are worried now that in a thermal bath I don't really have zero momenta. That's your point, right? Or
It's
yeah.
given there.
Hmm?
It's given there by the Bose-Einstein distribution. T squared plus.
No, sure, of course. Still, somehow that comes out of the. Yeah, I don't have an intuitive explanation. I have to think about it, but.
But particle distribution is there.
Sorry?
The particle distribution, he's asking where are the particles moving? Is that?
Yeah, of course. This is, in the end, this is what is here, of course. Yeah. No, but I think your point was that kind of in intermediate steps, I'm evaluating the 1PI, so I'm evaluating these diagrams. Right, I'm evaluating these diagrams here, so like these objects and so on and so forth.
So this is a constant in coordinates?
Exactly, it's a constant coordinate space, you get zero momentum. Exactly, so it's essentially this, exactly. So it's just the fact that you're looking at constant field configuration. So I think it exactly the same as at zero temperature. So
Yeah, I think I understand.
okay. Anything
Other
more?
questions? Okay.
Okay, so next time I will just finish this. It doesn't take too long, and then I will talk about tunneling, because that's the last thing we have to discuss before we can discuss cosmology. So that's the plan. Okay.
Aqui a
Misturando e tá
51 minutos.
misturando e tá
And
marcando.
our